Okay, to finish this particular proof, again, we just want to get to the heart of the argument. We're going to combine some steps, maybe leave out some things that might be necessary in a higher level mathematics class. But if you take a look at the given information in the diagram, it says the triangle ABC is isosceles, okay, with side or line segment AB congruent to line segment AC. So if you look over here at the diagram, this side AB is equal in measure or congruent to this side AC. So what we can say is that AB is congruent to AC. Now if you look over here, it says that GD is the perpendicular bisector of AB, so that's going to cut this in half. And it says that GE is a perpendicular bisector of AC, so that's going to cut this in half. In all actuality, we can put 2 marks on all of these because all 4 of these are congruent, because if AB is congruent to AC, then 1/2 of AB is congruent or equal to 1/2 of AC. And 1/2 of AB could be DB, and 1/2 of AC could be EC. So hopefully you understand the argument. That's really the most important part. But what that does is that gives us a congruent statement that DB is congruent to EC. Now the reason I was hoping to get to that point is because if you look here, we're trying to prove the triangle GDB is congruent to triangle GEC, and so that's why I wanted those particular segments stated to be congruent, because now we have a side and a side congruence statement. So if we were to put that in our proof, which we have to, we need that congruent statement. It's a side congruent statement. This part is not necessary, but at least we know what we're working with. I would say that we're going to say that's a combination of the multiplication property of equality, definition of bisector, and a little bit of substitution. Okay. Now again, if you were to write this as a paragraph proof, if you were to explain this and list the steps, that would be more than okay. Again, we're trying to get to the heart of the argument. So we know that DB is congruent to EC. Okay, again, using this idea of bisector. The other part we need to use is the fact that these are perpendicular. Perpendicular means they intersect at a right angle. Okay, so we know we're dealing with right triangles. With right triangles, now normally our possible reasons for triangle congruent to be side, 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 angle, side, angle, side, angle, 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 side, and in the special case of the right triangle, hypotenuse, leg. Now if you look at these right triangles, we know that the legs are congruent. Okay, we would probably want to state that angle GDB and angle GEC are right angles. You might think that this is a little unnecessary, and sometimes I think so too, but we need to get this down there so we can actually open ourselves up to use hypotenuse leg, because that's going to be the easiest and really in this case the one that makes the most sense. We're going to say that those are right angles by definition of perpendicular. That's what perpendicular means. It intersects to form right angles at the point of intersection. Okay, so now that we know those are right angles, the only thing that we have left to prove is that side GB is congruent to side GC. Well, if GD is a perpendicular bisector and so is GE, that means that these points, or this point G, has to be the circumcenter. Okay? And we know that any point that's on the circumcenter is equidistant from the vertices of the triangle, or in this case, this is a perpendicular bisector and so is this, then this would be as well. But it says that any point that's on the perpendicular bisector is equidistant from the vertices of the triangle. So in this case, GB would have to be congruent to line segment GC or side GC. So if we get that down there, what we can say is that line segment GB is congruent to line segment GC. And we could say, definition of circumcenter, or, let's say definition of circumcenter, because that's really not the perpendicular bisector's theorem, so we'll say definition of circumcenter. Again, maybe a little bit of a stretch there for that definition, but it gets the point across. We have another side congruent statement. Not only is this a side, in this case, this is the leg, and this is the hypotenuse of the right triangle. So we can prove these two triangles congruent by the hypotenuse leg congruence theorem. And I think that would be the best way to go about 8. Obviously, it's not the only way, and we did stretch some definitions, but we got the basic argument down there, and that's really what we're trying to get to. All based in fact, all statements based, we used all the given, they're all based on statements that were listed above. We weren't assuming or concluding anything that, in this case, we weren't allowed to do. So this works out, and this will be the second of the 2 possible proofs on the test. One of the 2 will be, the actual proof for credit, and the second one will be the bonus proof. So take a look. If you have questions, please send me an email or come see me in the morning.